All right, so let's finish out chapter 7, part 2. We've already gone over ionic bonding, covalent bonding, Lewis structures, and formal charges. So now that we have Lewis structures and symbols under our belt, what we're going to do is jump over to molecular structure because Lewis symbols and structures directly relate to molecular structure, and then we'll jump back and finish out the chapter looking at strengths of ionic and covalent bonds. So let's get started. So molecular shape. It's the shape and geometry of molecules are determined by their correct Lewis structure. So that's why we're going from Lewis structures to shapes because they're directly related to one another. So why does shape matter? Well, if you remember from chapter 1, we talked about how shapes of molecules defines its physical and chemical properties. So essentially how it acts and reacts in the chemical equations and reactions that we study. So, to dive deeper into how we determine shape of molecules, we essentially we can predict the shape by a very systematic approach. And what the important skill here that you need to know when determining shapes of molecules is that we need to count a molecule's counting the number of bonding and non-bonding electron pairs. So we will be talking a lot about electron pairs. When we look at electron pairs, we're typically looking at the bonding ones and the non-bonding ones. Or sometimes we call this lone pairs, lone pair. So I might call it a non-bonding electron pair or a lone pair. I mean the same thing. Um, so the numbers of the different electron pairs is what predicts the shape of a molecule. So here's some examples of different molecules. So this first example I have here is just a molecule with a formula of AB2. So this could be like CO2 or SO2, things like or H2O would actually also fit this this formula. So there are different molecules with the formula type AB2. Some molecules have a shape that are linear, some have a shape that are bent. So it's the difference in shape that can affect a molecule's chemical and physical properties. CO2 has different properties than H2O. One very obvious one is that CO2 is a gas at atmospheric pressure and temperature, and water, H2O, is typically a liquid at a typical room temperature. All right, and then here are just some other examples, like if I have a compound of AB3 type, um, so this could be like if it's charged or something, it could be like CO3 2 minus carbonate, or SO3 or PCl3, things like that. Um, with this type of formula type, where there's three different atoms around a central atom, we could have these three different molecule shapes here. So trigonal planar, trigonal pyramidal, and T-shaped. So this is just kind of like an appetizer to what we're going to be learning. So we will dive deeper into these shapes. I just want to show you that different shapes do exist for the same type of molecular formula. All right, so let's build some skills here. So what determines the shape of molecules? We already said that it's the number of electron pairs that defines the shape of a molecule, where those pairs could either be bonding or non-bonding. So I'm probably going to repeat this like a billion times, but it's very important that we distinguish between bonding electron pairs and non-bonding electron pairs. All right, so what determines shape of molecules? Well, since we're counting electron pairs, we need to think about how electrons behave. Remember, electrons are negatively charged, and so since they're negatively charged, they repel each other. And since these electrons exist in pairs in a valence shell, um, I'm going to say around an atom, around an atom. And again, it could either be non-bonding, bonding, or bonding. So since these electrons exist in pairs around a valence shell, the pairs will tend to repel one another. The pairs will repel one another. So that's why it's important to count the number, because it's that number of electron pairs that will define what shape you make, and we can predict the shape because we're assuming that electrons will repel one another as much as possible. So with this third point, all electron pairs on an atom will spread out as much as possible from one another to minimize the repulsion. So each, depending on the number of electron pairs, they will spread out around the central atom as much as possible to maximize the space each electron pair has. All right, and so we can predict the shape if we know how many bonding pair electrons and non-bonding electrons there are on an atom. So here are some different shapes. So if we have 2 electron pairs, they will spread out 180 degrees from one another. If we have 3 electron pairs, they will spread out in thirds around one another. So this is what we call a trigonal planar shape. And then the 2 electron pairs would be a linear. If we have 4 electron pairs, they will spread out from one another in 3D space, and this is what's called a tetrahedral shape. So this is 4 electron pairs. And then if there are 5 electron pairs, it makes a trigonal bipyramid shape. And then if there's 6 electron pairs, then it's an octahedral. So we will go through every single one of these examples. I'm just kind of giving you an introduction to it. So diving deeper into how we actually predict the shape, like how did I come up with these shapes with these electron domain numbers? This brings us to the theories that we use to predict molecular geometry. And what we use is what's called VSEPR theory, or valence shell electron pair repulsion theory. So this theory is pretty basic, but it works really, really well to predict molecular geometry. All right, so what this theory uses is it considers all of the electron domains around a central atom. So again, when we talk about electron domains, we mean all bonding electron pairs and lone pairs or non-bonding pairs of electrons. So we base this theory on how many electron domains are around the central atom, and we think about the repulsion between all these electron pairs equally. So let's just, I will finally define electron domain. So electron domains will be any region in which, we find, any regions in which we find valence electrons. And again, that means bonding pairs, bonding electron pairs, and non-bonding electron pairs, or lone pairs. Sometimes we call it lone pairs. All right, and so it's the number of electron domains that defines a molecule's electronic geometry. So electron domains define electronic geometry. So then that brings us into a molecular geometry. So molecular geometry, or the molecule shape, is determined by a molecule's molecular domain. So a molecule, I don't even have, do I have that? I don't have that definition. So let's just say molecular domain only looks at bonding regions, or you can think that it ignores lone pairs. Lone pairs. All right, so that's the molecular domain. The shape is made by the atoms and the bonds, not the lone pairs. So that's why we ignore lone pairs. And so this molecular shape will sit on top of the electronic geometry. So we can think of the electronic geometry as our parent structure, and when we start to ignore lone pairs, we essentially cover them up. So the overall shape doesn't change. We're just covering up portions of the electronic geometry to figure out what the molecular geometry is. And so VSEPR theory is a very simple but reliable method to predict these geometries. And so hopefully we will look at some examples here soon. But I need to show you a couple more definitions. All right. So how do we determine the number of electron domains and molecular domains? The most important skill you need in order to do this is drawing Lewis structures. So if you don't have a correct Lewis structure for a certain molecule, you will never get the electronic and molecular domains correct. So that is step number one, is that you need a correct Lewis structure for the molecule. Right? And usually when a question asks you about molecular domains or electronic domains, you're looking at one atom in the molecule. So typically, usually, it's the central atom, right? If there's a central atom, it's usually the central atom, but you're looking at one atom to determine the number of domains. All right. So moving on from that, so our definition for the number of electronic domains is the number of bonding domains plus the number of non-bonding non-bonding pairs or lone pairs. Sometimes we call it lone pairs. I'm just going to call it number of lone pairs. So what do I mean by bonding domain? Well, a bonding domain can either be a single bond, a double bond, or a triple bond. All of them count as one bonding domain. So since all of those bonding pairs, like for a triple bond, there are 6 electrons total or 3 bonding pairs, since they're all packed into one space, we just count that as one bonding domain. So essentially a bond of any order is only counts as one bonding domain. All right. So a bond of any order, so that means 1, 2, or 3 is any bonding domain. So then this relates directly to molecular domains. So the number of molecular domains is equal just to the we can kind of do this a couple ways. We can either say it's the number of electronic domains minus number of lone pairs. But if you look at the math that I have here, you can also say that the number of molecular domains is also equal to the number of bonding domains. So there's a couple ways you can think about it. This is number of lone pairs, because electronic domains is equal to number of bonding domains plus lone pairs, and then molecular domains is the previous line, number of domains minus lone pairs. You essentially can just cancel out and you're just left with bonding domain. So that's why the number of molecular domains is just equal to the number of bonding domains. All right. I think once we practice this, you'll see it. So let's just do a little bit of practice. Oh, and let me just point out, because of the math here, the number of molecular domains will never be more than the number of electronic domains. They can be the same number, but there can never be more molecular domains because we're always subtracting lone pairs. And the least amount of lone pairs you can have is 0. So either both those domain values are the same or moleculars is smaller. So you will see. So let's think about the central atom of these 4 examples. So nitrogen, carbon, oxygen, and sulfur. Let's count the electron or electronic domains and molecular domains. So remember, electron domains is number of bonding environments plus the number of lone pairs. So in nitrogen here, I see 1, 2, 3, 4 electron domains. So I can just write this. I see 3 bonding domains or bond pairs plus 1 lone pair. So this equals 4. So I'll just say 4. There's 4 electron domains here. And so remember, molecular domains is just equal to the number of bonding domains. Or you can think it's the number of electron domains minus number of lone pairs. So I see 1 lone pair in this molecule, in NH3. So I can either just subtract 1 lone pair from 4, so my answer here is 3, or you can just count the number of bonding domains. So there's three, because there's three NH bonds. All right, so this is an example where the electron domains and molecular domains are not the same. All right, so then for the next example, CH4. So carbon, I see that there are 4 bonds to carbon, 4 bonds to carbon. There are 0 lone pairs to carbon. So I'm going to say the electron domain is 4 and the molecular domain is also 4. Cool. So next one, oxygen. I see that there is, remember, we're just looking at bonding domains. So this bond counts as 1, the double bond counts as 1, and the single bond counts as 1. So I see 2 bonds total to that central oxygen, and I see 1 lone pair. So number of electron domains will be 3, number of molecular domains will be 2. All right, and then finally sulfur. So just remember that double bonds also count as 1 domain. If that was a triple bond, it would also count as 1 domain for bonds. And then last, sulfur, there is 4 bonds and 1 lone pair. And so I see total there will be 5 electron domains and 4 molecular domains. So this skill that I just showed you right now, being able to determine number of electron and molecular domains, super important with determining structure. So now let's dive a little bit deeper into all the different structures that we have with the different combinations of electron and molecular domains. So here is a table of common electron geometries, depending on the number of regions or number of electron domains around a central atom. So you totally need to memorize this table. Maybe rewrite it into your own words. That might help. We will get plenty of practice using these tables. So the most important thing here is across the top, we have the number of regions or the number of electron domains. So this first one, we have 2 regions, 3, then 4, 5, and 6. So electron domains 2, 3, 4, 5, and 6. These are the ones that we're going to talk about. And so you can see in spatial arrangement is how those electron domains will spread themselves out and repel each other around a central atom. So I want to take a note around central atom. And so our central atom here is this little dot, central atom. All right, so for 2, we have this full 180-degree arrangement. With 3 regions, we have it's flat and it's broken up into thirds. With 4, we have a tetrahedral, 5 a trigonal bipyramid, and 6 an octahedral. We will go into more detail about this. And so here is some line and dash wedge notation of these are just different ways to show you the same shape. So with a linear case, it's pretty easy to write that on paper when it's linear because a line is only in 2 dimensions. When we have 3 electron domains and it's trigonal planar, we can still write that on a piece of paper because that is also just in 2 dimensions. Where it gets a little hairy is when we have 4 electron domains and we have a tetrahedral. So a tetrahedral is spatially arranged in 3D space. So even this like little orange picture, it's kind of hard to see that like this lobe kind of comes out at you. These 2 lobes like come out and then the other ones kind of go back in, or I don't even know. It's kind of hard to see, but this shape is in 3 dimensions. So this line and dash notation is trying to convey to you 3D space. These 2 bonds, these 2 CH bonds are, I can say it's in the plane of the paper, and then this wedge comes out. So this hydrogen is coming out at you, while the dash goes into the paper. So just keep that in mind. Try to see it in your mind in 3D space that, you know, half of the molecule is in the plane of the paper, 1 hydrogen's popping out at you, and the other one's going back. So you can see that this molecule exists in 3D space. And then the same thing here for our 5 electron domain geometry. So there's 5 bonds around phosphorus. This T, the T is in the plane of the paper. One of the phosphoruses is popping out at you, and the other one's going back into the page. And this is called trigonal bipyramid. We will go into more detail. And then finally, octahedral, where there's 6 atoms or 6 electron domains around a central atom, the up and down north-south axes of the sulfur and fluorine bonds that's in the page, we have a set of 2 fluorines popping out of the page and 2 fluorines going back. All right, so what am I talking about now? All right, so these are actually what we call parent structures. It's a different color. These are parent geometries because we are only looking at the electronic structures. We aren't considering lone pairs yet, since we just are looking at the electronic geometries. We're not thinking about lone pairs. So this is what we call our parent geometry, and this is important in this next table. So this table shows the number of so it's kind of like the same table as the previous one, but now we are taking into account lone pairs. Lone pairs. All right. So here, this column is all the parent geometries from the previous table. And so what this table shows is, okay, if we start at 1, let's just start at this trigonal planar or something. So if we have a molecule with a 3 electron pairs, or 3 electron domains, I actually want to call this domains. Let's put it in red. So if there are 3 electron domains and 0, so what's important here is that there's 0 lone pairs. The electron geometry and the molecular geometry will be the same. So if 0 lone pairs, then electron geometry and molecular geometry are the same. So that is what this first column is. When there's 0 lone pairs, the electron geometry and molecular geometry are the same. All right, so once you define the electron geometry, you don't have to adjust anything in the molecule to figure out the molecular geometry because they're the same. So then where things change is if we have 3, oh, this is dead again. So where things change is when we have 1 lone pair in our Lewis structure. And so what happens is we replace one of the electron domains with a lone pair, and we only consider the shape made by molecules. So in this case, when there are 3 electron domains and 1 lone pair, so the molecular domain equals 2 in this case, our shape is bent, or sometimes they call angular, but I call it bent. All right, and so we can kind of do the same thing for if we have 4 electron domains. If we have 0 lone pairs, our electron domain and molecular domain is the same, so our shape is tetrahedral. So molecular domain equals 4. If there's 1 lone pair, our molecular domain is equal to 3. So we just replace one of the electron domains with a lone pair, and we just consider the shape made by the atoms. So this is we call trigonal pyramid. And then finally, if there are 2 lone pairs, our molecular domain is equal to 2. So we replace 2 of the tetrahedral electron domains into lone pairs, and we're back to a bent shape. So we will go through all of these. So I just wanted to this is the table, the summary of everything, but we will go into details with all of them.